All right, we are moving into 10.2 logarithmic functions. So what we have here first, it says write the logarithmic equation in exponential form. So what I do is I like to call it the snail. So we start at the base, we snail around to the 3, and we end with the big number. So the exponential of this, the base is 4, raised to the third equals 64. Number 2, I need a snail, so I'm going to start at the base, pick up the number, and end with the big number. So 3 to the 4th equals 81. Again, start with the base, pick up the number, then you get your answer. 7 to the negative 2 is 149. 1 over 49. Snail, base, answer, 16 raised to the 3/4 equals 8. Snail around answer, 36 raised to the 1/2 equals 6. Now this one doesn't have a base. There's no small number right here. So when there's no base, it's actually a 10. So it's going to be 10 to the negative 3 equals 1 over 1,000. Okay. Okay, that's not what I wanted to do. Okay, much better. All right, number 7, write the exponential into logarithmic. So again, it's the snail. So snail, snail, snail. So it's going to be the log. The first thing is a 5, then it snails around to 125, and then it ends with the 3. Again, base, answer, exponent. Log of 8, then it's 64, curls around to the 2. Again, base, answer, exponent. Log of 81, 3 is 1/4. Again, snail, snail, snail. Log 9, 27, it's 3 over 2. Again, log 6, 1 over 36 is negative 2. Again, log 4, 1 over 64 is negative 3. Log 7 of 1 is 0. Again, log 10 is negative 3. Okay, not too bad. Yep, 15. All right, it says evaluate the logarithmic expression without a calculator. So what that means, evaluate means solve. So we need to solve this thing for x. So I'm going to do the snail. 4 to the what is 4. So now I'm going to write it out. 4 to what power equals 4. So I snailed base, answer, exponent. Base, exponent, answer. So 4 to the x is 4. So x has to be 1 for this equation here. Same thing, set it equal to x. Do your snail, base, around there. So it says 2 raised to the x is 32. 2 to the what power is 32? 5th? I think I'm right. X equals 5. Yeah, 5th power. 2 to the 5th is 32. Again, equals x. Snail, small, around, around. 6 to the x equals 1. The only way to make this a 1 is if x was 0, because everything to the 0 power becomes 1. Snail. 3 to the x equals 81. 4? I don't remember. Let me double check. 3 raised to the 4th? Yes, yes. Okay, natural log and e are inverses. They make each other cancel. So ln and e will cancel. They're inverses. That's like saying 1 times 1/2. No, it's like saying 2 times 1/2. They would just cancel because they're inverses of each other. And that just leaves me with the number 3. I'm going to rewrite this as ln e to the negative 1 because 1 over e is really saying e to the negative 1. Now, ln and e will cancel, leaving you with the number negative 1. I'm going to rewrite 21, ln e to the 1/4. Square root of 4 is the same as 1/4. ln and e will cancel, leaving you with a 4th. Okay? This log, there's an invisible 10 here. Goes back to what we were doing with 15 to 17. We have to put an x here. Whenever they're real numbers, we do the snail. 10, my base, raised to the x, equals 10,000. What is that, 10 to the 3rd? Nope, 10 to the 4th. Duh. Yeah. Okay, number 7, we're going to go the other way. I'm going to rewrite it the other way. I think that there's a shortcut here, though. So base, answer, exponent. So 7. Yeah, no, that's how this works. So log 7 with a base of 7, like this guy right here is a base, and this right here is a base, so these will actually just cancel, leaving you with just the number 3. Same thing here. This thing has a base of 10, and there's a 10 here and a 10 here, so the answer is just 1/2. Just like before, e and ln cancel, leaving you with its number, which is 6. And once again, e and ln cancel, leaving you with the number 1/5. Okay? Next page. 27. Solve the equation by changing it to an exponential first. Easy. This needs a 10, or else it doesn't work. Has to have a base there, so its base is 10. Now I can snail. So 10 to the 2nd power equals x. Well, obviously, 10 to the 2nd power is 100, so 100 equals x. Same thing, there's a 10 there. Base, go around. 10 to the 4th equals x. 10 to the 4th, we just said, is 10,000. Kind of an ugly 4. Again, base 10. 10 to the negative 1 is x. Negative exponent just puts it in the denominator. We've got a base here, so we can snail. 100 to the 1/2 equals x. 1/2 is the same as saying the square root. Square root of 100 is 10. Not too bad. Okay, describe how to transform the function log of x or natural log of x into the graphs given below. So this is just like what we did on that last paper for 10.1. The rules apply. If a number is with x, it's left, right. If a number is in the front or in the back, it's up, down. Ready? So 31, the number here is with the x, so it's going to move it to the left 3. This number is the same as if I said -1 in the back. -1 plus is the same as just a -1 in the back. So if it's subtracting 1 in the back, that means we're going down 1. A +2 in the back, easy, up 2. Now this here, the negative with x, we said in the last worksheet that this is a reflect over the y-axis. A negative in the front is a reflect over the x-axis. Notice this is not -2 plus log. This is -2 times log, which is different from what happened here. So in number 34, a number in front is called a vertical stretch. Okay, 35. +3, obviously up 3, because it's a +3 in the back. And negative over the x is always reflect over the y. Super ugly. +1 goes up 1. Negative is reflect over x. A 3 is a vertical stretch. Now this guy here is really saying negative x plus 1. I rewrote it as negative x plus 1. Now this is minus 1. Because I need this 1 to be positive. Sorry. So this negative is a reflect over y. And this number with the x moves it to the right one. 36 is pretty difficult. Okay, let's try the next one. 37, now we go into graphing. So to graph a function, the best way to do it is to take your parent function and then just shift left, right, up, down from the parent function. Now for logs though, it doesn't have the same parent function because this base is 2, this base is 3. So graphing these is actually a little bit more difficult than the last page, than 10.1. And we also can't just plug it in the calculator because the base is not 10. I can't just put negative log x minus 3 because it has a base here of 3, which we cannot type into most calculators. Of course, there are some fancy calculators that'll do it, but for your average calculator, it will not let you change a log basis number. Okay, so what I'm going to do first is let us know what the parent function is for the natural log of x. So the parent function for ln of x, you can go to y equals, type in ln x. So for the natural log of x, it actually does not touch 0. So the first number of natural log is 1. So we're going to graph 1 and 2. Let's go this way. I need some room. So if you tried to graph 0, it wouldn't work. There is no natural log of 0. So it would give you an error. But there is a natural log of 1. And the natural log of 1 is 0. Natural log of 2 is 0.7. Natural log of 3 is 1.1. So I plugged it in the calculator, press second table, and then I can now memorize this is my natural log parent function. Natural log of x. Okay, so now I take the parent function and I change it based on my numbers. This says take your x's and go the opposite of the sign. So that's x plus 2. So I'm going to go through and add 2. Plus 2, plus 2, plus 2. Now I don't need my original x's of the parent function. Now it says take your y values and add 5. Plus 5, plus 5, plus 5. Okay, so I took my parent function and I changed my x's and y's. Now I can graph 1, 2, 3, comma 1, 2, 3, 4, 5. 4, comma 5.7. 5, comma 6.1. Okay, so my natural log function is going to look like this. So it has a line here that looks like this. So just like we said for the last unit, my asymptote is the number in the back. So 1, 2, 3, 4, 5. So my asymptote is y equals 5. So notice it doesn't go below 5. My domain again is all real numbers. And my range is that we start at 5 and we go up forever. Okay, number 38. So again, in number 38, I need a parent function. So I'm going to draw a table. The parent function is y equals log base 2 to the x. So now this is where things get a little weird. So I'm going to rewrite this. Let's see the easiest way to explain this. So what we did on the first page with logs is if it was written as a log, I put the log in the front, and then I do the snail. So we do the same thing. 2 to the y equals x. So with log functions, instead of putting my regular numbers in for x, I'm going to put my regular numbers in for y. So I'm going to put -1, 0, and 1. A log function is the inverse. It switches x and y from your exponential functions. So now I'm going to plug it in. 2 raised to the y value, my first y value is -1. 2 to the -1 is just 1/2. Next, 2 to the 0. Anything to the 0 power is just 1. Next, 2 to the 1. Anything to the first power is just itself. So that's the parent function for y equals log base 2. So now I take the parent function and I shift it according to what it says. It says take your x values and add 1. So it's 1 and 1/2, 2 and 3. Then it says take your y values and add 2. So that's 1, 2, and 3. So now I can graph this. Right 1.5, up 1. Right 2, up 2. Right 3, up 3. Kind of weird. So my log function, just like natural log, very similar, it's going to look like this. So my asymptote, hold on one second. You know, my asymptotes are actually these numbers, +2, right? Yeah, so because this is inverse, your asymptote is actually the inverse. So it's x equals 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Does not make any sense here. It does here. So my asymptote here for sure is 2. Hold on a second. 2. Hold on. I'm looking at this graph. One moment. So in your calculator, if you go to math, at the very bottom is A, which says log base. So you could plug these into y equals and do it that way. Okay, so again, my domain is always, ooh, you know what? Your domain here is not negative infinity to positive infinity. Your domain here starts at 1, 2, 3. Yep. And this one here, my domain starts at 1, 2. My range starts at 1 to infinity. That's not, what am I doing? To infinity, sorry. There we go. Okay, so my asymptote for this one here is the number in the back. It's an x equals, so it's x is 2. Just like so. It doesn't pass the line x equals 2. Okay, so let's do number 39. 39 is a little bit more difficult. I'm going to erase some of 38, so we've got some more room. In fact, I'm going to just zoom in. Too big. Let's just erase all this. All right, so I'm 39. So what I have here is my parent function, y equals log base 3 of x. So that's your base. But remember what we said about logs. I'm going to put the log in the front and the y in the back, so that way you can snail to turn this into an exponential to get rid of the log. So this equation is actually 3 raised to the y equals x. So I can make a parent function table. Very easy. My y value is now my input. So I'm going to plug in -1, 0, and 1. So that's like saying 3, the first y value is -1. A negative makes me flip my base. Then it says take that 3 and raise it to the 0. 3 to the 0 is the number 1. And it says take that 3 and raise it to the 1. 3 to the 1 is just 3. So that's the parent function of this table right here. However, I'm not just done with the parent function. There's a number in the back and there's a number in the front. There's nothing that's actually in parentheses with the x. There's no x change because there's no parentheses with x. So what this negative does is we're going to multiply my y's times negative. So negative, so that makes it 1, 0, negative 1. Then it says take that y value and subtract 3. So that's negative 2, negative 3, and negative 4. Okay, so now I graph. Right 1/3, down 2. Right 1, down 3. Right 3, down 4. It's negative, it flipped over the x-axis, it reflected. So my domain here is my first x value. Is 1/3. And then it goes to the right forever. You may want to photo math this one just to check. So in these, this does not make a difference in my asymptote because it's an inverse, so that doesn't matter in my asymptote. My range is my y's. My y values live from negative 2, no, negative infinity, and it stops at negative 2. So then my asymptote is the number x equals 1/3. Asymptote. Okay? 39. Let's look at 40. So 40 takes us back to another natural log function. So we did this parent function earlier, x and y. So for a natural log function, we said that it doesn't touch 0. So my ordered pairs start at 1. So it's 1, 0, 2.7, 3, 1.1. So I'm going to take these numbers and I'm going to change it based on this. So it says take the x values and add 2 because it's the opposite of the sign. So it's 3, 4, 5. Then it says take the y values and add 5 because there's a plus 5 in the back. So that's 5, 5.7, 6.7. This the one we just did? It is, so I guess we literally just did this. 37 is done. Whoops, I put it twice, my bad. Okay, 41, still useful. Natural log starts at 1. So for the 14th time, it's 1, 0, 2.7, 3, 1.1. We take our numbers and we change them. Minus 2, so that's negative 1, 0, and 1. We take my y values and I multiply times negative. That's 0, negative 0.7, and negative 1.1. So I'm going to graph it. Those I don't need. But I'm going to rewrite it so it makes more sense. So the new one was negative 1, 0, 0, negative 0.7, and 1, negative 1.1. So I started with my parent function, and then I shifted my numbers based on where they were. Now I can graph. Left 1, down 0.7, down 1.1. Nope, that's not right. So it's actually going to go this way because it's negative. Okay, so my domain is my x's. This number here is x equals 2. So that's my asymptote. So my x's are from negative infinity. Oh my gosh, I keep doing my infinity sideways. To positive 2. My range is negative 0.7 to infinity. I'm double checking that. 1 second. So it is negative natural log of x plus 2. Make sure it does not put that in parentheses. Of x plus 2. Graph. Negative natural log of x plus 2. Yeah, it is in parentheses. Done. Okay, so I was right the first time. So in this one here, oh my goodness, come back. Here we go. So these ordered pairs are correct. So it's negative 1, 0, 0.7, 1, negative 1.1. So this one here is actually going to go like this, because it's a reflection over the x-axis. So my asymptote is negative 2, because whenever you have something with the x, it's always the opposite of the sign. So x equals negative 2. And my range is that it's going to go from negative 0.7. Yeah, that's the biggest y value. Negative 1, 0, 0, negative 0.7, negative 1.1, negative 1, 0, negative 2. Doesn't go from there. So that's 0. Double check my ranges here, because these are not pretty. Okay, so for number 41, we already found the parent function for, this is the parent function here is y equals log base 2 of x. So we have our base. So 2 to the y equals x. So again, we take our y as negative 1, 0, 1. We did this earlier. This became 1/2. This was a 1, and this was a 2. So now from here, we're going to change our x's and y's. My only x change is that we're subtracting 1, because it's the opposite of the sign. So this is negative 1/2. This is 0, and this is 1. My y change is I have a negative, and then I have a minus 2. So I'm going to multiply times negative 1. And then I'm going to subtract 2. So now I can graph my function. Left half down 1. 0, negative 2. 1, negative 3. So it starts here, and it drops, reflection over the x. So my smallest x value here, my asymptote is always an x for this type of function. So whatever's with the x, you change the sign. So its x is negative 1. Maybe my domain here is off. So we switched it. So our domain has to be from negative 2 to infinity. Your domain here is going to be your asymptote to infinity. My range is the lowest y value. The lowest y value here is negative 1. So it's actually negative infinity. And it stops at negative 1. Okay? This video is about to die, so I'm going to leave 42 for you. Use the same XY table there, though, and then I'll make one more video for the last ones. So go ahead and try these.